Good morning, student. So today this is our sixth and last lecture on gravitation, and in our today's lecture we will discuss three important bits. Number one, weightlessness. This condition is filled by an astronaut in a satellite. The second one, what is the time period of revolution of a satellite around the planet, and the last one, the binding energy of an orbiting satellite. Now, as far as this weightlessness condition filled by an astronaut in a satellite is concerned, in order to restrict our discussion, already I had just drawn some point. Now, you know very well that according to Newton's second law of motion, F is equal to what? M into A, where F is force acting on an object of mass M, which is moving with an acceleration A. Moving with an acceleration A. Now, in our day-to-day life, we know that when a passenger is standing either in a lift, look at this, or a passenger is standing on an elevator. Have you seen the elevator? Either at what? Railway station or in shopping mall. You had seen the elevator so that you can move automatically in upward direction or in downward direction. So, passenger in both the cases, how many forces will act on the passenger? Only two forces will act. One of the force is the gravitational force, which is equal to its weight mg, and which is acting downward towards the earth, while the another force which is acting on passenger, it is the normal reaction N exerted by the floor of a lift or a floor of an elevator. Means passenger is acted upon by two forces which are exactly opposite in direction. Now, because these two forces, they are exactly opposite in direction, so here we are having two possibility. Here we are having what? Two possibility. If I say passenger is acted upon by what? Net downward force, means this downward force mg must be greater than normal reaction. So I can say that net downward force F suffix d is equal to. Now, how to find the net downward force? Because you have one force is in downward direction, other force is in upward direction. Net force is in downward direction only when mg is greater than n. So, net downward force acting on that passenger is mg minus of n. The second possibility, if I say that passenger undergoes acceleration in upward direction, or the net force acting on passenger is what? In upward direction, means this normal reaction must be greater than what? Its weight. So, the net upward force acting on a passenger F suffix u is equal to n minus of mg, because upward force is greater, means normal reaction n is greater than that of what? Its weight mg. Now, remember why we are having the feeling of weight of our body. Every person will have a feeling of weight only because, or why this passenger feels the weight? Because of what? Only because of normal reaction exerted by the floor of a lift or the floor of an elevator on a passenger. So, the normal reaction exerted on the passenger either by the floor of lift or by the floor of an elevator is responsible for feeling of weight of our body. Means n is responsible, and due to n only we can have feeling of weight of our body. And as far as this normal reaction is concerned, it is the relative difference. It is normal reaction N is equal to F minus of mg. F may be F upward, F may be F downward. It means this F may be ma. So normal reaction N, it is the relative force between the motion of a body and a motion of a lift. Motion of a body and motion of a lift. See here, N is equal to F minus of mg. So normal reaction is what? Normal reaction is the relative force between the motion of body and motion of an object. Now let us consider one by one that lift is having a zero acceleration. First case, suppose here lift is having zero acceleration. This happens only when I say that lift is having zero acceleration, it means either that lift is stationary. Stationary means its velocity is zero, or that lift will move either in upward direction or in downward direction with constant velocity, with constant speed or constant velocity. Lift is having zero acceleration, it means, or this happens only under two conditions, either that lift is stationary or that lift is moving upward or in downward direction with uniform velocity. Remember, when velocity is constant means acceleration is zero. Acceleration is what? Zero. So you can use downward force or upward force. So what is the net force acting? F, which is equal to m into a. But a itself is zero. So F is equal to what? Zero. As F is equal to 0, therefore, what you can say? But F is equal to mg minus n. 0 is equal to mg minus n. Therefore, n is equal to what? Mg. N is equal to mg. Means the normal reaction acting on a passenger is equal to its weight. It means if passenger is standing on a weighing machine in a lift or in an elevator, if a passenger is standing on a weighing machine in a lift or on elevator, and if the net acceleration of that lift is zero, means that lift is either stationary or moving upward or downward with constant velocity, then the normal reaction acting on a passenger equal to its weight, then under this condition that passenger feels his normal weight. That passenger feels his normal weight means that weighing machine will measure the weight which is equal to the actual weight of a passenger. Means the weight measured by that weighing machine is equal to the actual weight of a passenger. Condition required is that lift must have a zero acceleration. Lift is having what? Zero acceleration. Now the second probability, that lift having net upward acceleration. Now acceleration, what is needed for acceleration? There must be increase in velocity. Suppose here lift is at the bottom. What is the velocity of lift? Zero. Let this lift starts moving in upward direction, and after some time it will reaches a velocity v. Or lift is moving in downward direction, and before it come to rest at the bottom, its velocity is v equal to v, and when it come to rest, its velocity v becomes equal to what? 0. When I say lift is having net upward acceleration, means what is needed? Lift must move in what? Lift must move in upward direction. Lift must move in what? Upward direction. It means lift just starts moving in upward direction from the lower floor. From the lower floor, when lift starts moving in upward direction means its velocity will increases. So that lift is having what? Upward acceleration, because it is moving in upward direction, velocity is increasing. Similarly, that lift will have an upward acceleration when it is about to stop. When it is about to stop when it is moving in what? Downward direction at the lower floor. Means initially V equal to V, that lift is moving in downward direction, then V becomes equal to 0. Because here velocity is decreasing during its downward motion, means that lift undergoes retardation. And what is the direction of retardation? In a downward direction. Means what is the direction of acceleration? Opposite, that is in upward direction. So you remember that when I say that lift is having net upward acceleration, this happens in two cases: when lift just starts moving in upward direction, or it is about to stop while moving in downward direction at the lower floor. At the lower floor, means in both the cases, as far as net acceleration of that lift is concerned, how is that net acceleration? Upward. So the net force acting on lift is what? Upward force. So out of these two formula, we will use F upward is equal to N minus of mg, and upward force F upward is equal to what? M into A upward. Put this value here in this equation, therefore M into AU is equal to N minus mg, or N is equal to, take this mg to this side, N is equal to mg plus MAU. Here what you can say? N is greater than the actual weight of passenger. N here it is mg plus MAU. Means whenever lift is having net upward acceleration, the normal reaction exerted by the floor on the passenger is greater than its weight. So that's why that passenger feels heavier. It is not the apparent feeling of passenger, it is the actual reading shown by that weighing machine. Means weighing machine will record the weight which is greater than the actual weight. Means here the weight measured by that weighing machine is greater than the actual weight. Is greater than what? Is greater than the actual weight mg. Third possibility, lift having net downward acceleration. You know, for acceleration what is needed? Increase in velocity. So this happens at the top of the floor when that lift starts moving in a downward direction. When lift is at the top, velocity of lift is 0. When lift just starts moving in downward direction, it may attain a velocity v. So lift can have net downward acceleration AD when that lift starts moving in a downward direction from the top floor, or when lift is about to stop at the highest floor. Lift is about to stop. About to stop means here lift is having velocity v, and when it reaches to the highest floor, its velocity becomes 0. So you may say that lift is undergoing retardation. Okay. But what is the direction of retardation? Upward direction. Means what is the direction of acceleration? Downward. So lift can have a net downward acceleration in two cases. That is when lift just starts moving in a downward direction from the top floor, or when lift is about to stop. Lift is about to stop when it reaches to what? The highest floor. So in this case, because net acceleration of lift is downward, means net force is what? Downward. So net force is downward, means Fd is equal to mg minus of n. Which formula is useful? Net downward force, it is mg minus n. Mg minus n. But the downward force, because F is equal to ma, so net downward force is equal to mass of a passenger into acceleration of lift in a downward direction. So you can put this value in this equation. So you will have MAD is equal to mg minus of n. Take this n to this side. So n is equal to mg minus of MAD. And from this what you can say? N is a normal reaction acting on a passenger is less than its actual weight. So that's why that passenger in the lift which is having a net downward acceleration will have a feeling of what? Lighter. He feels that his weight is what? Somewhat light. So passenger have a feeling of lighter weight when that lift is having what? Net downward acceleration. Net downward acceleration. This is not the apparent feeling by a passenger, but it is what? The weight measured by weighing machine when the net acceleration of lift is what? In a downward direction. That weighing machine will record the weight of passenger which is less than that of its actual weight. Means here you can say that the weight measured is less than the actual weight mg of an passenger. Now there is one more case, state of free fall. What is state of free fall? We know that you can move the lift up and down with the help of cable. And when lift is at the top and suppose by mistake that cable is broken, then both passenger and lift both starts moving freely under gravity. Means both passenger and lift they are moving in what? Downward direction. So it is a special case of what? Downward acceleration. And what is that downward acceleration? AD is equal to acceleration due to gravity G. So when the cable of a lift is broken suddenly, then both passenger and lift they starts moving in a downward direction with an acceleration AD equal to G. AD equal to what? G. Now what is the formula force? Formula for downward force? FD is equal to mg minus of n. But FD, force in a downward direction, it is mass into acceleration in downward direction, that is mg minus of n. But AD equal to G for the case of what? State of free fall. Acceleration in a downward direction equal to acceleration due to gravity. So that's why here m into g becomes equal to mg minus of n. Naturally this n becomes equal to 0. Means when the cable of a lift is broken and both passenger and lift they will fall freely under gravity with an acceleration AD equal to G, then because the floor of a lift or a floor of an elevator will not exert any normal reaction on the passenger, so he has a feeling of weightlessness. This condition is called condition of zero gravity. So whenever cable of lift is broken and passenger is falling freely under gravity, always as no normal reaction is acting on that passenger by the floor of the lift, so that's why that passenger has a feeling of weightlessness. And this is the heading of our topic of discussion, that why a person or under what condition a person will have a feeling of weightlessness. Remember, feeling of weight is mainly due to what? The normal reaction exerted by the floor on the person's body. Now again you know, because we want to discuss why the astronaut in the satellite will have a feeling of weightlessness. For that purpose we must know this condition of what? State of free fall. So see here, as far as astronauts are concerned, we know that astronaut in a satellite, they are performing what? Circular motion. We know that satellite is revolving around the planet. Means satellite is performing circular motion. For an object to perform a circular motion, that object must be acted upon by what? centripetal force, means that object must be acted upon by a centripetal acceleration, and the necessary centripetal acceleration required for circular motion of satellite, it is provided by acceleration due to gravity g at the location of a satellite. If satellite is at this location and g is acceleration due to gravity at that location, means both satellite as well as that astronaut, they are acted upon by an acceleration g. They are acted upon by what? An acceleration g. This is a case of state of free fall, means AD equal to what? AD is equal to G. And when AD is equal to G, the net normal reaction or the normal reaction acting on an astronaut is 0, means the floor of satellite will not exert any normal reaction on the satellite or on the astronaut, and because no normal reaction is acting on an astronaut by the floor of that satellite, so that's why astronaut in a satellite will have a feeling of weightlessness. Or you can say that sometimes you had seen in the Hollywood movie that astronauts, they are just flying in the space, flying in the air. Why it is so? Because of what? Because those astronauts, those astronauts, they are acted upon by what? Downward acceleration. So it is our expectation that astronauts, they must fall on the surface of Earth. But this will not happen. Why it is so? Because astronauts, they are performing circular motion, because astronauts were lying in a satellite and satellite is performing circular motion. During the circular motion, we know that when object is performing circular motion, how is the direction of tangential, how is the direction of their velocity? It is tangential to the circle. So the astronaut, they continues to perform what? A circular motion instead of falling on the surface of Earth. So this is about weightlessness in a satellite. So as far as possible in board examination, you will try to write down the answer to such type of question as minimum as possible with the help of maximum formula. You simply discuss these formula and the 4 cases one after the other. Now we will see what is the time period of orbiting of a satellite. Now let us define what is time period of a satellite. You know very well that satellite is performing circular motion round the planet Earth. So the time period of satellite, it is a time taken by a satellite to complete one revolution round the Earth. The time taken by a satellite to complete one revolution round the Earth is called time period of satellite. So here already I had drawn a diagram where this is our planet Earth. Let capital M, it represent mass of an Earth, and capital R, it is radius of Earth. Suppose we are having a satellite of mass M, satellite of mass small m. First, that satellite of mass small m, it is projected vertically upward to a height h above the surface of Earth, and then that satellite has given a horizontal velocity of projection which is equal to its what? Critical velocity. A satellite of mass small m projected vertically upward to a height h above the surface of Earth, and then that satellite has given a horizontal velocity of projection equal to its critical velocity. What is critical velocity? It is the horizontal velocity of projection given to a satellite above the height h above the surface of Earth, for which that satellite revolves in what? A circular orbit. So see here, what is the radius of circular orbit? When that satellite has given a horizontal velocity of projection equal to critical velocity, no doubt it starts revolving in a circular orbit. Now what is the radius of a circular orbit? Radius of a circular orbit is radius of Earth plus height above which that satellite is projected. So small r equal to r plus h, radius of Earth, plus the height above the surface of Earth to which that satellite is lifted. So radius of circular orbit of satellite is r equal to r plus h. See here, time taken by a satellite to complete one revolution around the Earth is called its periodic time, or is called its time period. Now in one revolution, what is the distance traced by a satellite? Satellite traces a distance equal to what? Circumference of a circular orbit of radius r equal to r plus h. So I can say here Vc is the critical speed of a satellite. The distance traced by a satellite in one revolution equal to circumference of circular orbit, and the time taken by a satellite to complete one revolution is called its time period. So therefore, as we know, speed is equal to distance upon time. Speed is equal to what? Distance divided by time. Now here satellite is moving with a critical speed Vc equal to, what is the distance covered by satellite in one revolution? That in one revolution, satellite covers a distance equal to what? Equal to circumference of circular orbit of radius r plus h divided by the time taken for one complete revolution. It is called as the time period of a satellite. Speed equal to distance upon time. Critical speed equal to circumference of circular orbit divided by time period. What is the circumference of circle? 2 pi r of radius r. So what is the circumference of circular orbit of radius small r? Circumference is 2 pi into small r. Time period of satellite, let it be denoted by t, and critical speed is Vc. Therefore, time period t is equal to 2 pi r divided by Vc. But we know the formula for critical speed. What is the formula for critical speed of a satellite which is revolving in a circular orbit of radius r? Critical speed Vc equal to under root of gm divided by radius of circular orbit. Radius of circular orbit. So put this value of Vc in this equation. This is equation number 1. This is equation number 2. So let us put the value of Vc. So we will get under root of gm divided by small r is equal to 2 pi r divided by t. Squaring on both the sides. So on after squaring we will get gm divided by r is equal to 4 pi square r square divided by what? T square. Take this t square on one side. So t square is equal to 4 pi square r square, and this r, it becomes r cube. 4 pi square r cube divided by gm. Remember, 4 is constant, pi is constant, universal gravitational constant capital G is constant, and mass of Earth m is constant. It means here you can draw the conclusion that t square is directly proportional to r cube. Now how to read it? That the square of period of revolution of satellite around the Earth is directly proportional to cube of radius of circular orbit around which that satellite is revolving around the Earth. Square of period of revolution of satellite, is directly proportional to cube of radius of circular orbit of a satellite. Cube of radius of what? Circular orbit of a satellite. Now you can write down the expression for time period. See, you are taking square root on both the side. So t becomes equal to 4 pi square. What is the square root of 4 pi square? It is 2 pi. And in under root, it is r cube divided by gm. So the time period of revolution of a satellite, it is t equal to 2 pi under root of r cube divided by what? Gm. 2 pi r cube divided by gm, or t is equal to 2 pi under root of r plus h whole cube divided by gm. And from this expression, remember, the time period of revolution of satellite, it does not depends on mass of satellite. Is there any factor small m, mass of satellite? No. Means the time period of satellite does not depends on mass of satellite, but period of revolution of satellite, it depends on mass of earth. It depends on radius of circular orbit. It depends on the height h above the surface of earth. And also you remember that as the height h goes on increases, the period of revolution of satellite will also goes on increases. Period of revolution of satellite also goes on increases. As we know that acceleration due to gravity at a height h, gh is equal to gm is equal to what? Gh into r plus h whole square. So gh is equal to, or gm is equal to gh into r plus h whole square, because acceleration due to gravity on the surface of earth, it is g equal to gm divided by what? R square. So gh is equal to gm divided by what? R plus h whole square, or gm is equal to gh into r plus h whole square. So because satellite is at a height h, actually the distance of that satellite from the center of the earth is what? R plus h. So gm is equal to, so acceleration due to gravity acting on satellite at a height h is gh. So you can replace gm by gh into r plus h whole square. So this t becomes equal to 2 pi under root of r plus h whole cube divided by this gh into r plus h whole square, or this is equal to 2 pi under root of r plus h, see here, cube and this square. So r plus h divided by what? Gh. So time period t can be expressed as 2 pi under root of r plus h upon gh, or you can write t is equal to 2 pi under root of r divided by gh. 2 pi under root of r divided by gh. Now in case when satellite, there is a special case. If I say satellite is revolving very close to the surface of earth, when I say that satellite is revolving close to the surface of earth, it means h is very small as compared to that of radius of earth. It means r plus h, it can be approximately taken to be equal to what? R. It means the period of revolution of satellite, which is revolving very close to the surface of earth, it can be written as t equal to 2 pi under root of r divided by what? G. Not gh, it is g. T equal to 2 pi under root of r divided by g. So this is all about the time period of a satellite which is revolving round the earth. Now the last and the most important bit, that is binding energy of an orbiting satellite. Now what is the binding energy of an orbiting satellite? So let us see here, we are having our planet Earth. Let capital M is the mass of Earth and R represent radius of Earth. A satellite of mass small m, it is projected vertically upward so that it attains a height h above the surface of Earth. And when it attains a height h, that satellite has given a horizontal velocity of projection which is equal to what? Its critical velocity, so that satellite, it starts revolving in a circular orbit round the Earth. What is the radius of this circular orbit? Satellite will revolve in a circular orbit of radius small r equal to r plus h from this to this. See here, this height is h and this radius is what? R. So r plus h, it is the net radius of circular orbit in which that satellite of mass m is revolving. Now, as far as the binding energy is concerned, it is defined as the minimum amount of energy that must be given to a satellite in order to escape the satellite from Earth's gravitational influence. The minimum amount of energy that must be given to a satellite in order to escape it from Earth's gravitational influence, it is called binding energy of a satellite. So here we are having a situation, a satellite of mass m first projected to a height h above the surface of Earth and then given a horizontal velocity of projection equal to its critical velocity. So that satellite revolves in a circular orbit of radius r equal to r plus h. Because your satellite is performing circular motion, it has both kinetic energy as well as what? Potential energy. Now, can you tell me what is the kinetic energy of a satellite? Kinetic energy of a satellite is equal to, what is formula for kinetic energy? Half mv square. So here kinetic energy of satellite, it is half of mass of satellite small m into square of velocity. What is the velocity of satellite? It is vc, critical speed. So half m into what? vc square. But we know what is vc? Critical speed of a satellite is equal to under root of gm divided by r, or vc square is equal to gm divided by r. Therefore, this kinetic energy is equal to half of small m into this vc square, means it is gm divided by r, or simply it is gmm divided by 2r. gmm divided by 2r. So the kinetic energy of a satellite revolving in a circular orbit of radius small r, it is gmm divided by 2r. Now you know what is the gravitational potential at any point at a distance small r from the center of the earth? Gravitational potential at distance r, at a distance small r from what? From Earth center. At a distance small r from Earth center, what is that gravitational potential? It is equal to minus of gm divided by r, minus of gm divided by r. Now, we want to find out what is the potential energy of a satellite. As you know, potential energy of a satellite, potential energy of satellite is equal to gravitational potential multiplied by mass of a satellite, multiplied by mass of satellite. What is gravitational potential? Minus gm divided by r. Mass of satellite is m. So net potential energy of satellite is minus gmm divided by r. See here, kinetic energy is equal to what? Half of, or kinetic energy is what? gmm divided by 2r. Potential energy of satellite is what? Minus gmm divided by r. Therefore, total energy of satellite is equal to kinetic energy plus potential energy. Kinetic energy is what? gmm divided by, see here I can write this as gmm, half gmm upon 2r. So 1 by 2 gmm upon r plus potential energy, but here potential energy is negative, so it is minus gmm divided by r. You can take GMM divided by R is taken as common. So what is left in bracket? 1 by 2 minus 1, which is equal to minus GMM divided by 2R. Half minus 1 means minus 1 by 2. So this is the total energy of a satellite is equal to minus half of GMM divided by R. This is the total energy of what? A satellite revolving in a circular orbit round the earth in a circular orbit of radius R. See here, we want to escape the satellite. Here in the expression for total energy, you can see there is an occurrence of negative sign. What that occurrence of negative sign indicates? That satellite is bound to the earth due to its what? Gravitational influence. But binding energy is the amount of energy, minimum energy that must be given to satellite in order to escape the satellite from Earth's gravitational influence. So, in order to, because satellite is having total energy minus half GMM upon R. So, to escape the satellite from Earth's gravitational influence, you must have to supply certain minimum energy. And that minimum energy that must be supplied to escape the satellite from Earth's gravitational influence, it is a negative of total energy, and that is equal to minus of minus GMM divided by R, or you can say binding energy of satellite is equal to GMM divided by R. Binding energy of a satellite revolving in a circular orbit round the earth, it is given by expression GMM upon R. Always remember, binding energy is a negative of total energy. Binding energy is what? Negative of total energy. Again, you can have different cases. Binding energy is equal to GMM divided by small r means R plus H. Special case, when satellite is revolving close to the surface of earth. When satellite revolves close to the surface of earth, then H is very small as compared to that of radius of earth. Or binding energy of a satellite revolving close to the surface of earth, it is BE, binding energy equal to GMM divided by R. GMM divided by R.